Hello everybody, welcome back to our virtual classroom and another lesson in our trades training video series. I'm Joe Carswell, and this session is going to cover parts used in the electrical process. We're going to go through all the pieces and materials you would commonly see when you're installing electrical in a residential structure. So let's get right into it. To begin, I'm going to work us through the parts, starting with the outside of the building, the service coming in, how the electricity works through the system, and we're going to work it all the way through the finished stages where it's going to be cover plates and what happens at the very end of the process. To start with, one of the first parts that's going to be installed on a building is going to be the meter base. This is going to have a meter installed in it. This is how the utility company is going to measure how much electricity is being used by a specific customer. It's going to record it, and then this information can be transferred to the company to then get billed to the customer. So this is typically going to be a metal enclosure where this meter base is going to get plugged in. The next component that will be in the system will be a breaker panel. You might hear this called a load center or a service panel. This is where all of this electricity is going to come into, and we're going to distribute it from this box to all of our separate circuits in the structure. In this box will be a ton of what we call circuit breakers. These are simple switches that are going to have two functions. One is going to be, it's a manual disconnect that we as the user can turn on and off if we want to isolate or break power to a specific circuit, maybe a device in the building. And it also works as an automatic shutoff switch if there's a problem with the circuit. And as you can see, there is this manual switch on this breaker. It has a very hard sound to it. So it's a very positive switch. And if it switches automatically, there's internal parts that will sense if this switch is carrying too much amperage or too large of a load. It's going to turn this breaker off to protect the wire and all the devices that are on this circuit. So this breaker, there's some common parts of a circuit breaker. That's going to be, there'll be a terminal connection or a clamp here that you're going to tighten onto typically what's going to be your black or hot wire. That's going to go in here. You'll tighten this terminal up, and it's going to clamp down very tightly on that wire. There's also going to be a connection in back that will fit into the panel. This is how the service panel is going to transfer the current from its bus bars to this switch through into the circuit. You also will have, this is a single pole breaker, which means there's only one wire connecting to it, and it's going to send 110 voltage out through to the circuit. This is a double pole breaker. This one, as you can see, has two terminals on it, and there will be two wires that will come in here to connect. This is fastened, or it's bridged. So this is a double pole breaker that's bridged. This is typically for a situation where you have an appliance that requires two hot legs coming into it. This is a little more advanced wiring than we need to talk about here, but just keep in mind that breakers can take up one space or two spaces depending on the configuration of the circuit. A typical breaker is going to monitor amperage. We can get into specialized breakers. These ones will have circuitry in them that can then look for other things going on in the circuit. This particular one is called a GFCI, which is a ground fault circuit interrupter. The circuitry in this breaker is very specialized. It's looking or monitoring the current that's going out of this breaker, and it's also monitoring current coming back. It's measuring the two, and if it finds that there's an imbalance in this measurement, it's going to trip this breaker. It's going to shut this breaker off. It's going to kill the power, and what that's going to do is to save the user from a potential of electrical shock. This is a safety feature built into this breaker, and we're also going to see this safety feature later in some of the end of circuit devices. Another type of special breaker that has safety features built in is an arc fault circuit interrupter. This AFCI is going to also monitor the current as well, but what it's looking for is problems in the circuit. It's monitoring resistance in the circuit. This can lead to problems with arcing, and arcing leads to fire in a building. And electrical fire can be a real problem, so this circuit is a safety circuit that's going to be installed to help prevent that. At the moment that it senses problems in resistance in the circuit, it's going to trip this breaker. Next up are materials that will be involved in the process of installing electrical are going to be wires. We have a lot of wires, and to begin with, we have a service wire. A service wire is going to be a heavy gauge wire that's going to carry power into the building. It might carry power from our meter base to our breaker panel or from the street to our meter base. These are typically going to be aluminum wire. They're going to be multi-strand, they're going to be wound together, and they're going to have a heavy insulation on the outside of it. The reason they're made of aluminum, if we're talking about two main materials for wire, we're going to have copper and we're going to have aluminum. So our aluminum wire is going to be a little less expensive for our larger conductors. This makes a lot of sense. There's pros and cons to copper and aluminum, so let's talk about that. So to take a close look at this service wire, I have my conductors inside, which are typically bundled together. I have them pulled apart so that you can see the separate strands. If they weren't pulled apart, they would look more like this end, very tightly wound. So aside from a stranded wire, you might have a solid wire. Here you see, this is what we call Romex. It has 3 solid conductors inside of it. So a solid wire is going to offer less resistance than a stranded wire. It's also going to be less flexible than a stranded wire. A stranded wire is going to allow that wire to bend and move more freely. And there is only one piece of metal in a solid wire. So think of a stranded wire as multi-solid wires twisted together. We can make those strands smaller and achieve the same gauge rating. We're going to talk about gauge in a minute. Here is an example of that stranded wire. You see these multi-small conductors. That's going to give flexibility to this wire. Typically, when we're installing electrical, you're going to see stranded wire when you get to the fixtures that are being installed. These will need a lot of flexibility in those conductors, and therefore the stranded wire makes a lot of sense. One thing about stranded wire to mention is that the gauge, because of the resistance being a little higher in stranded wire, the gauge has to be a little thicker than your typical solid wire. So if we're talking about gauge, what does that mean? There's no mystery here. Gauge is basically just talking about the thickness of the wire. The trick, or when some people get confused, is that the smaller the number of the wire, the larger the gauge. So here you see 3 very common gauges of wires used in residential electrical systems. You see a 14 gauge wire, which is your smallest wire. You see a 12 gauge wire, which is a medium size. And then you see a 10 gauge wire, which is the largest. So a 10 gauge wire is going to handle more amperage or more volume of current than a 14 gauge wire. Actually, it's rated for twice as much as a 14 gauge wire. 14 gauge wire is rated at 15 amps, 12 gauge wire is rated at 20 amps, and 10 gauge wire is rated at 30 amps. So you can see here, as the gauge increases, the amount of amperage they're rated to handle also increases. Now we can talk about wire materials, now that we understand gauge, stranded, and solid variations of wires. So as I mentioned before, 2 main materials that we're going to make our conductors or our wire out of. This is copper. I would say copper is considered the favorite. It is the best conductor of electricity. It's also the most expensive. It's soft, it's flexible. It has very low resistance to the transfer of current. It happens to be more expensive than aluminum. This comes into play as to what we use which material for in the electrical system. But let's take a look at that aluminum wire. So here is that service wire I talked about. These are much larger gauge conductors. This is going to carry a lot of power into our building. It might be from the street to the meter. It could be from the meter to the service box. And also for some of our larger appliances, you may see stranded aluminum wire. The plus is that it's less expensive than the copper material, but it's going to offer more resistance to that electrical flow. So what that means is that we have to design for this. And so if we use aluminum wire, we have to use special connections, special considerations with this wire that we don't have to with copper. So if you're designing or working with aluminum, you have to understand that you have to match components to the aluminum that work with that special material. So Romex is one of the most common cable types used in a residential electrical system. What Romex is specially designed cable, and I call it cable because this is a jacketed bundle of conductors. Our conductors are going to be solid wire inside of a plastic jacket. That's our Romex cable. It's labeled NM, which is going to mean non-metallic. It's a plastic jacket that is going to offer some protection, but is very soft and easily removed. So we have to take care when we're installing the Romex that we don't damage this jacket. It also offers some insulation from electricity, so we need to keep that intact. So as you see here, what's highlighted on the presentation is 14 gauge Romex cable. This is a 2-conductor cable. The reason we're calling this a 2-conductor cable, and I have an example of that right here, is that it has 2 insulated conductors, but it also has a bare copper wire in the center of it. The reason for the bare copper wire is not for an electrical reason to carry electricity. It is a safety feature built in that if we have a problem with the circuit, it's going to act as a way for the system to recognize there's a problem and to trip those breakers we talked about in the breaker panel. So consider your bare copper ground wire not as a conductor, but as a safety feature that's built in. So this is a 14 gauge 2-conductor wire. We're going to call it a 14-2. It's rated at 15 amps. Here is that same gauge Romex, but they're adding another conductor to it. So as you see here, we not only have the black conductor, like in the 14-2, and the white conductor, both insulated. We also have the bare copper ground, and they've added a red insulated wire. That will be a second conductor that we can use for specialized wiring. And we'll talk a little bit more about that in electrical process. That wire also, just so you know, is rated at the same 15 amps. So a 14 gauge wire is always rated at 15 amps. You can move on to a larger gauge Romex wire. And if you notice, the jackets of the Romex are color coded so that at a glance, an inspector or the installer can identify which gauge wire they're working with. So the 14 gauge wire is always going to be a white jacket. The 12 gauge wire is going to be a yellow jacket. And this one is also available in a 14-2, which is going to have 2 conductors, your black, your white. It's also going to have the bare ground. We're not going to count that, so that's a 12-2. It's rated at 20 amps. And there's also a version just like the 14-3 with a 3-conductor, and it's going to add the red insulated wire as an additional wire to use for running circuits. If you move down to a 10 gauge wire, then what you see here is 10-2 and 10-3. We've upped the thickness of the wires so these can handle up to 30 amps for whatever circuit we're running. It's also important to mention that all of our devices that we're connecting at the beginning and the end of this cable will have to be rated at the same amperage. So a 12 gauge wire will need 20 amp rated devices connected to it and a 20 amp breaker. A 10 gauge Romex will require a 30 amp breaker and 30 amp rated devices at the end of it. And a 14 gauge wire will require 15 amp devices and breakers. Now that we've run all our cables, there's a lot of spliced ends that we need to connect. We need to protect those spliced ends in a box. This is very important electrical code we need to follow. It's for safety reasons and also some practical reasons. So we need a box. We're going to call it a junction box. It could be metal or plastic. They're going to come in a lot of different shapes and sizes, and they will serve to, number one, house any electrical or wire connections that we have to make. It's also going to give us a place to mount our devices, whether that's a switch or a receptacle or even a light fixture, could be a smoke detector. Any of our devices also need a box to mount to. So I've got here a single gang box that's going to be made for one device. So if I have, say, a switch, this box is going to be a perfect size for one single switch. It also could have an outlet. It also could have any other device that we're working with. And these boxes have on the back of them knockouts or places that we can knock out. This is where our cable is going to enter in. So our Romex will go into the back of this box, and that, once it enters, we're going to strip those wires and then make our connections to our other wires or to our devices. As I mentioned, this is a single gang box. Think of that as one space. We have a double gang box. That's going to be 2 spaces. We also have a triple gang box. That's going to allow us to put 3 devices in this box. That could be 3 switches, 3 outlets, 3 anything. So you have 1, 2, 3. You may even have a round box. These are typically found in ceilings where you're installing fixtures. This type box has what are called wire clamps in them. And these are sort of a pinching or clamping device that once we push the Romex in, it's going to lock it in place. It can't come out. That helps hold the wire and keep that cable from coming out. What we don't want is for this cable or the bare conductors pulling outside of this enclosure. Remember, this enclosure is to protect those wires and keep them from being exposed outside. When we're mounting these boxes, there's a couple different styles I have here that we can talk about. So as you see, each one of these boxes has 2 nails. These nails are going to get driven into the framing. So the box will get set forward and these nails will get driven in. That's going to hold that box tight. This arrangement of nails expects that we're going to be right next to a stud. Another version of a mount for a junction box is going to be a flange. This flange would set right flat on the stud. We would then nail through it to hold this junction box in place. Now that we've run our cables, we have our junction boxes in place, we need to nail these wires down. We need them secure, and we don't want any of these parts moving around once we've installed them. That's only going to lead to loose wire connections, which then will cause us problems later. So we're going to use wire staples to hold this Romex very tight to the framing. This is just your basic staple, run-of-the-mill steel staple. This one here offers a little more protection. You can see it's coated or dipped on the top with a little bit of plastic. That's going to help protect that Romex jacket when we hammer this down onto that cable. This one offers a little bit of plastic insulation that's also going to protect our staple a little bit, or our Romex cable. And this one is a little different variation. You don't see these in the field a lot, but you might use this in one of your skills exercises. This has a plastic bridge and 2 separate nails. It's very difficult using this one to actually do any damage to the Romex cable jacket at all. One other way to secure wires that's pictured in our presentation is going to be the harness type. This one nails to the framing, and then as you can see, you can install several cables in it. It snaps shut and holds those cables in place. There are some rules to go by when you're installing wire staples. One of the rules is that you need a staple within 12 inches of every box. So every cable that goes into that box needs a staple within 12 inches. Typically, you're going to use 1 staple per cable. So that would mean you can't stack the cables under them unless you're using this harness type. If you're not near the entrance of a junction box, you'll need a wire staple at least every 54 inches everywhere else. This is a great image of a wire staple that has been driven properly. It's securing this Romex cable. It's not driven too far, and it's doing its job. It's going to hold that cable in place. When we're wiring, we often have to make splices between two wires. So we're going to twist those wires together. We need something to keep them tight, to clamp them together. That's what a wire nut does. So if you're splicing two wires together, you're going to use this particular type of hardware to do that. Wire nuts come color-coded. They're going to come in different sizes, and they're going to accept different gauges and numbers of wires depending on the size of them and their rating. So here you see the inside of a wire nut. They get twisted onto a wire. And the way that happens is we're going to take that wire and we're going to screw it on like we're screwing on a nut or a bolt. It's going to go on in a clockwise direction, and it's clamping down on those wires that are already twisted together. That's going to guarantee that we keep a nice tight connection, which is going to allow good flow of electricity through those two wires, and it's going to guarantee we don't have a problem later with them coming loose. Another important job when we're installing electrical is protecting those wires. If you remember, we're talking about wood framing. We have to run these cables through our wood framing, and there are other materials that are going to get added later. A lot of those materials will be added with fasteners. Those fasteners are going to enter into our framing. We have to share the space with all of these wires and cables we've run. And if those cables are too close to the front edge of that framing, we might put a fastener through that cable. That could end up being a short, could end up as a fire or a shock hazard. So we're going to use a nail plate to protect our cables if they're too close to the edge. As you can see here, a nail plate is nothing more than a steel plate that's got some thickness to it. There's no fastener that will be able to penetrate this, and it's got some spikes on it. These spikes will get hammered into the framing, and you can see a picture of this. Here we see a good image of a nail plate in use. It's protecting this Romex cable that's pulled through the framing behind it. This is the end of part one of our electrical materials. Make sure you catch the follow-up, part two. We're going to get into some more pieces and parts we will use to install an electrical system. This video is a production of Trade Skills U, all rights reserved.